Pressure forces atoms to occupy smaller volume. Macroscopic properties of minerals, such as density, are defined by their atomic configuration. Ultra-high pressure metamorphism is characterized by minerals and polymorphs of greater than 2.5 gigapascals of pressure, with increasing coordination numbers and density. These include coesite, schistosite, and diamond. High pressures are common in the mantle, but need special conditions to occur at Earth's surface. Since the discovery of coesite in a meteor crater, over 20 localities of ultra-high pressure metamorphism have been found. High-pressure subductions such as the Himalayas, meteorite impacts which can produce diamonds in the crater, and kimberlite pipes of South Africa.
We're just going to look at bolide impacts and kimberlite pipes because they're awesome.
Coesite is metastable at low pressures. It should revert back into quartz in its retrograde to the surface. There are four main reasons for the preservation of coesite in a rock's retrograde path. These are coesite inclusions in a strong mineral, rapid esquimation, cooling during decompression, and finally, fluid infiltration. Coesite can be preserved within inclusions of minerals such as garnet and zircons, which act as pressure vessels. Secondly, coesite is an anhydrous mineral, with studies concluding that it contains almost zero water. As pressures increased, water is expelled from the rock, allowing coesite to form instead of quartz. Fractures that form when the rock is decompressed fill with water and start to change the coesite closest to the cracks. Also, for the survival of coesite, water intrusions must only happen in low temperature conditions. Furthermore, water can be trapped within a coesite inclusion when it forms, allowing the water to partially change the mineral into quartz when pressure decreases. Finally, rapid esquimation and cooling during decompression are attributed to coesite's preservation. However, not enough data is available to fully explain coesite preservation.
Depends on the impact angle, velocity, and the mass of meteorites. Impact pressure can vary enormously. Therefore, impact metamorphism has a larger range of UHP minerals products than UHP subduction metamorphism. Fine-grained coesite in quartz-bearing sandstones is the first UHP mineral sample found in nature. When the meteorite hits the surface, some terrestrial grains melted while squeezing water out from melt quartz grains, anhydrous coesite then slowly formed inside the impact melt. If the impact pressure is higher, diamond may crystallize, and melt quartz grains will form a denser crystal structure than coesite and finally become the dense mineral called stisophyte. Unlike coesite, stisophyte is difficult to produce within the UHP range of recyclable subduction material in the asthenosphere unless there is a deep subduction occurring at 350 km below in Earth. The highest grade lateral quartz polymorph observed thus far is a superdense extraterrestrial crystal found in India called sapphire, formed between 30 to 80 gigapascal. However, in most situations, terrestrial quartz grains will lose their crystal lattice and break down into diaplectic glasses instead of forming UHP minerals if the pressure exceeds 35 gigapascal. This extreme UHP mineral is actually very rare, be found either on the surface or inside the asthenosphere.
For something different. Kimberlite pipes form by rapidly moving material working its way through the continental cratonic lithosphere and erupting in a marrow zone at the surface, leaving behind a carrot-shaped feature filled with breccia, glass, and a carrot filling of high matrix percentage of xenochrys and phenochrys, including olivine, dunite, and xenochrys of diamonds. That was what you mined here. While there are a range of hypotheses on the formation and parament of kimberlites, check them out below, not enough time here, but it is mostly anhydrous conditions. Incidentally, good enough for the coesite in the silicic melt to form. Provided there is an appropriate assumed geothermal gradient, the xenochrys can be used to reconstruct the mantle profile at the time of emplacement. For instance, a nodule of grosbanite containing coesite and sandine with a pressure of 2.9 gigapascals and 900 degrees Celsius on that event. Inside the diamonds are inclusions of chemically diverse suites of eclidate minerals. It's inconclusive to find the source rock. Diamonds themselves survive the eruption due to rapid decompression and drop in temperature, effectively freezing the magma during the eruption. Go diamonds! For more information on ultra-high pressure, check out the reference list and look out for the 2015 GEOS3101 ultra-high pressure video installment.